This presentation is delivered by the Stanford Center for Professional Development.
Okay. The saga continues. All right, let me remind you what we did last time. Last time, I introduced the best class of functions for Fourier transforms, or at least I asserted that it was the best class of functions for Fourier transforms. And I want to remind you what the properties are, and I want to tell you what we're going to do with it. So, the best class of functions for Fourier transforms. And we call that S the class of rapidly decreasing functions and they're characterized by two properties. They're infinitely differentiable, and any derivative decays faster than any power of x. I will write that down. So first of all, 1, phi of x, I think I called last time f. This time I think I'll call it phi because I'm going to be tending to use that term, that letter, in a lot of the discussion. Doesn't matter. We have to be flexible in our alphabets. Phi of x is infinitely differentiable, so as smooth as you could want. Has as many derivatives as you can want and more, differentiable. And secondly, that, as I said, any derivative decreases faster than any power of x. So let me write that down and then say another word about it. For any m and n greater than or equal to 0, x to the n dn dx to the n, the nth derivative of phi of x in absolute value, also tends to 0 as x tends to plus or minus infinity. Those two properties. Let's see if I got that right. Yes, infinitely differentiable, and this says that any derivative, this is the m, say, m. I don't know whether I used m and n that last time this way or the other way. It doesn't matter. And m and n are independent here, so this says like the third. Now, there's nothing mysterious here. You got to measure decay or growth some way, and the simplest way of measuring growth is in powers of x. You can say a function grows linearly, or grows quadratically, or grows cubically, whatever. That's a natural scale of measurement for how a function is growing. And so, to talk about a function decreasing more rapidly than any power of x, you can say, well, if it decreases faster than linearly, then x times that function is going to go to 0. If it decreases faster than quadratically, you look at x squared times the function, you want that to go to 0 as x tends to plus or minus infinity. So multiplying by a positive power of x and insisting that the product of the positive power times any derivative here tends to 0 says that it goes to 0 faster than any power of x. It's a strong statement, but it's not an unreasonable statement. All right? And as it turns out, there are plenty of functions that satisfy this property. What wasn't obvious by any means, and again, nature provides you with so many different phenomena, how do you pick out the one really to base your definition on? You know, why this for properties of Fourier transforms as the best class of functions for Fourier transforms and not something else? Well, I say genius is what genius does, and as it turns out, this was the right class to single out in the following sense. And even here, and it may not be completely clear that this is what you really need, and that the story will spin out as we go on. So why the best for Fourier? Well, one reason is that if phi is a rapidly decreasing function, then so is its Fourier transform. Is also in S. All right. That is, if the function decreases faster than any power of x, and any derivative decreases faster than any power of x, so is true for the Fourier transform. Also, if the function is infinitely differentiable, so is its Fourier transform. All the properties are preserved. All those analytical properties are preserved by Fourier transforms. That's very important. Again, why is this so important, and why these particular things work so smoothly for developing the theory, you'll see. And the second property is that Fourier inversion works. That is, if phi is in S, then the Fourier transform, the inverse Fourier transform, the Fourier transform of phi is equal to phi. And the same if I go the other direction. That is, the Fourier transform, the inverse Fourier transform of phi is also equal to phi. And I mean the usual Fourier transform here defined in terms of the integral. Right? And there's no problem with that integral converging because the function is dying off. All right. So that's where we were last time. But if this is such a darn fine class of signals for the Fourier transform, how come it doesn't include some of the signals we would really like it to include? Like, for instance, the most basic example of all, the rectangle function. All right, the rectangle function is not in, so why? But if so good, if S is so good, for instance, the rectangle function is not in S. The most basic example. It's not in S because it's not continuous. Never mind differentiable or anything else, it's not even continuous. The triangle function is not in S. It's continuous, but it's not differentiable. You know, the examples that we started our whole study on don't even fit into this supposed class of the best functions for Fourier transforms. And not to mention the other class of functions that we might want to consider, like constant functions, sines and cosines, and so on. None of those are in the class S. Constant functions, trig functions, many others are not in S. All right? So how do you resolve this? That is, how do you get to defining the Fourier transform, or how do you get back to, how are we sure we haven't lost anything, and then what is gained by considering this very good class? So how can we be sure, or assured, maybe I should say, we haven't lost anything? I mean, it looks on the surface that we've lost something by restricting ourselves to consider this class when we've lost the rectangle function, we've lost the triangle function, who knows what else? Lost anything. And furthermore, and have gained and will gain even greater generality. All right, so that takes a little while to tell that story. And we'll get most of the way there today. But answering that question causes us to take up another strain of development that was happening around the same time. All right, so to answer this, we have to pick up another line of development. Another line of development. The two will come together triumphantly, but only after we follow this path for a little while. And that is delta functions and so on and so on. It is the idea of generalized functions, so-called generalized functions. They're also referred to as distributions, and that's probably the term that I'll use, also known as and this use of the word distribution has nothing to do with the way we used it earlier when we talked about probability. It's just one of those clashes of terminology that comes up every now and then. You can't do anything about it. There are only so many words to go around, and I don't know. Actually, I don't know the origin of the word distribution in this context, but that's what's used. So generalized function distribution are synonymous terms, and I'll probably find myself slipping into using distribution rather than generalized function, although both terms are in current use. And what I mean by here is, so i.e., or typified by the delta function, the Dirac delta function, which really should be called the Heaviside delta function. Dirac delta. Now, I am assuming, and I will remind you of some of the properties that you probably have seen. I'm assuming that you've seen the delta function in various contexts, because everybody that goes through an engineering course on signals and systems, anybody who goes through a quantum mechanics course, and I don't know where else it comes up, but it's one of those things you learn to use operationally. And maybe you feel a little queasy about it, you know, but nevertheless, it gets the job done somehow, and you'd rather not worry about somehow those fine points that all the statements you're making are complete bullshit. All right, so what are those statements that are complete bullshit? You often see it defined this way. A, delta of x is equal to 0 for x different from 0, but 0, it's infinity. B, the integral from minus infinity to infinity of delta of x dx is equal to 1. This function, which is 0 everywhere except at one point, and its total integral is equal to 1. And C, if I integrate the delta against any other function f of x, I get the value, I'll call it phi, just to, since I'm using that term, I get the value at 0. Quite remarkable indeed. Every one of these statements is a complete bullshit. All right, there's just no way to make any of this make sense precisely. But there's something there. All right, there's something there. People who used it with some skill were able to do so without avoiding any of the pitfalls. And there are possible pitfalls. I mean, you can manipulate deltas incorrectly, and you can make mistakes. All right, but those masters, classical masters, Heaviside, some other that followed him, and Dirac, in particular, in his applications of quantum mechanics, could make sense of these things and use them effectively. But no one, and because they got the right answers and because they were so effective operationally, nobody wanted to admit that these statements were all complete bullshit. So what is to be done? There's only so much of that you can stand. I mean, some people have higher thresholds than others, but at some point it had to be cleaned up. There are still, there's still cases of this around. There are very important cases of this around. The one that people cite most often now are Feynman integrals, Feynman path integrals for quantum electrodynamics, I guess, is where they're used. I mean, nobody can make sense of them mathematically, but you can't deny that they work. All right, and it is now an acutely felt challenge to somehow give a rigorous foundation for Feynman path integrals. It doesn't exist yet, as far as I know. I don't think there's any way of doing it. It's the same sort of thing. In the right hands, you can effectively compute with them, but feel a little queasy about it somehow. Now, the fact is that operationally you can understand what's going on here. All right, delta is supposed to represent a function which is concentrated at a point. All right, and this was probably even said to you when you first learned about delta. And there are various ways of approaching this. All right. And you may have seen some of these. I'll give you a sample calculation or an example of this. So various ways of doing this. But it always involves a limiting process. It's always via a limiting process. All right, so for example, what I mean by a limiting process is what you do is consider typically families of legitimate functions that are getting narrower and narrower and still satisfy these sort of basic properties. So, and I say there are various ways of doing it, but let me give you one very simple one. E.g., you consider a one-parameter family of shrinking rectangle functions or concentrating rectangle functions. Consider a one-parameter family of rectangle functions. All right, I'll write it down. So I'm going to look at 1 over epsilon pi epsilon of x. All right, now that's the family that I want to consider, and the parameter here is epsilon, and I think of epsilon as small as tending to 0, ultimately tending to 0. Now, what do those functions look like? Well, the rectangle function, we know what that looks like, and it's not hard to see what happens when you scale it like that. The ordinary rectangle function, again, is 1 between minus a half, and never mind what happens at the endpoints. That's not important here. It's 1 between minus a half, and it's 0 outside that interval. That's pi of x. If I scale it, 1 over epsilon pi epsilon of x, that function is 1 from minus epsilon over 2 to epsilon over 2. So again, I'm thinking of epsilon as being small here. And if I multiply by 1 over epsilon, I'm making it large in the vertical direction. So the height is 1 over epsilon. All right, that's what the graph of that looks like. And it's still the case that the area is 1. If I integrate this function, I get 1. If I integrate this function, it's the area of the rectangle. The rectangle has base epsilon and height 1 over epsilon. The area is 1. As epsilon is getting smaller and smaller, it is approximating what you think of as an ideally concentrated function. those properties defining, at least the first two properties defining the delta function. It's 0. Again, think of epsilon getting smaller, so it's centering around the origin here, centering around 0. So it's non-zero. It's 0 outside a small interval around the origin. It's becoming steeper and steeper right at the origin. And what about the final? Well, let me write down. Its integral is equal to 1. Integral from minus infinity to infinity of pi epsilon of x dx is 1 over epsilon, the integral from minus epsilon over 2 to epsilon over 2, 1 dx. That's the only place where it's non-zero. That's equal to 1. All right. And what about that final property? If I integrate this scaled rectangle function against a function phi of x, what happens? All right. So if I look at the integral from minus infinity to infinity of pi epsilon of x times phi of x dx, what happens there? Well, let's take the case where phi is smooth enough, say. You can actually do it more generally, but just to get a simple idea. Imagine expanding phi in a Taylor series expansion. That is, write this as, so again, this is 0 except on the interval from minus epsilon over 2 to epsilon over 2. So this is equal to the integral from minus epsilon over 2 to epsilon over 2 of phi of x dx. Okay? Now imagine writing phi, or it's because pi of x is equal to 1 there, and it's equal to 0 outside that interval. So that's equal to 1 over epsilon, the integral from minus epsilon over 2 to epsilon over 2. Say, write phi of x as phi of 0 plus phi prime of 0 times x plus and so on, higher order terms. I'm thinking about the Taylor series expansion. That's assuming the function is smooth. You can do it. You can write a similar argument if the function is only continuous, but never mind that. I mean, I just want to see what the point is here. Why it's concentrating. All right, so if I integrate that, and then I get higher order term, put one more term in here. Phi double prime of 0 over 2 times x squared plus and so on, higher order terms, integrated with respect to x. All right, what happens if I carry out the integration? Well, the first term, that's phi of 0. Phi of 0 times the integral of 1 from minus epsilon over 2 to epsilon over 2, 1 over epsilon, that just integrates to 1. And then the second term, what happens here? Well, this is a constant, so on. If I integrate x, I get x squared, all right? So I'm going to get epsilon squareds here times 1 over epsilon. That's going to give me a term of order epsilon. If I integrate x squared, I'm going to get an x cubed. And if I evaluate it between minus epsilon over 2 and epsilon over 2, I'm going to get terms of order epsilon cubed times 1 over epsilon. That's going to give me terms of order epsilon squared. All right? So the result is that beyond the first term, beyond the constant term here, I'm going to get terms of order epsilon, or higher order terms. All right? Epsilon, epsilon squared, epsilon cubed, and so on and so on. So what happens as epsilon tends to 0, this term goes away. Okay? So as epsilon goes to 0, you can say that the limit as epsilon goes to 0, this tends to phi of 0. That is to say, the limit as epsilon tends to 0 of this integral, 1 over epsilon, the integral from minus epsilon over 2, epsilon over 2, pi epsilon. Oh, no, we can do it like this. Let me write the whole thing down here. The integral from minus infinity to infinity of pi epsilon of x, phi of x dx, that's the integral that I just computed, is equal to phi of 0. All right, that's what's meant by concentration via a limiting process. Now, again, I'm assuming, actually, you can tell me if I'm wrong, that you probably saw this calculation at some point. I mean, when somebody was trying to justify the delta function and somebody talked about it as somehow ideal concentration, they probably looked at it pretty much in this way. All right, so again, just to make sure you see you understand what the issue is here. Okay, to say this, to consider this, the limit as epsilon tends to 0, 1 over epsilon pi epsilon of x. To consider this limit of this function, this sequence of functions, depending on the parameter epsilon, it makes no sense. All right, to consider this limit makes no sense. All right, but to consider operationally what it means when I integrate this scaled function against an ordinary function and take the limit of the integral, that does make sense, and it produces the value constant to the value at 0. this limit, epsilon tends to 0, the integral from minus infinity to infinity, or I'll do it like I did before. Pi epsilon of x, phi of x, dx. And to say that that's equal to phi of 0, this does make sense. Okay? All right, that's okay. And the fact is, by experience, the ways that delta appeared in applications weren't so much this way, or naked, just as sort of a limit of a sequence of functions. Really, it occurred operationally when it was paired with another function, when it was paired with a legitimate function, and somehow the idea was by a limiting process you were concentrating things and you were just pulling out the value at the origin, say. All right? That's really operationally how it appeared. And that was an extremely important thing to realize. All right, so these statements somehow, again, individually, these statements just don't make sense and can't be made to make sense. All right, but in practice, the way it was used, you replace delta, you replace what you think of as idealized delta by some sequence of functions which are concentrating, and you consider them as paired with a function via integration, and then you can do everything you want to do in a context that you have a certain amount of confidence in. Yeah.
Is there a 1 over sigma there?
Pardon me?
If outside the integral, is there a 1 over sigma?
Where? Here?
Yeah.
No, because I define pi. I guess I define. Yeah, 1 over. Yeah, thank you. Sorry, 1 over epsilon. Sorry. Thank you. Yeah, thank you. Okay. All right. Now, we're almost there. All right, and once again, this is one of these tipping points where you look at the accumulated body of evidence. You say to yourself, what's really going on here? And again, the mathematical modus operandi somehow is to turn the solution of a problem into the definition, to turn it around. Yeah. Sorry.
It should. 1 by.
Yeah, it should. Yeah, it should. You scale this thing, right? This doesn't make sense. I mean, this should be there. This 1 over epsilon should be there. Pardon me?
You missed it out in there.
Did I mess it up somewhere else?
On the first.
Up there. Right here. Okay. Now is everything okay?
Over there.
Over where?
Just tiny.
Up there? No.
No.
Cut! Trouble is, I guess I was thinking of the scale. When I put the scale in here, I was thinking of that as also scaling the outside, and I was wrong there. I'm sorry. But everything's okay. Is everything okay now? I'm just going to walk back and forth here 1 or 2 more times, and then collect myself. I don't expect the camera to follow me. And maybe once more. Okay. All right. All right. Now. This was a big conceptual step. And again, it follows the mathematical modus operandi of turning the solution of a problem into a definition. So we're going to concentrate, instead of concentrating on somehow the limiting behavior and so on, the idea is to concentrate on the operational effect or the outcome of concentration in one case, and then more generally, more general operations. All right? So I want to change the point of view. It really requires a fundamental change of point of view here. So to capture this idea and to include much more, and how it's going to include much more, again, I'll have to explain to you in just a second. All right? And to include more, we need a change of point of view. We need a really fundamental change of point of view. All right, it becomes operational. It becomes an emphasis on the outcome rather than, sort of the process. All right, the focus is on the outcome. Rather than on the process. What I mean by this is, in the case of delta, the outcome was At the end of the day, it concentrated and pairing this approximating function, this approximating sequence of functions, gave you the value of the function you were interested in at 0, and that had to be done. The process was taking a limit. Right? There was a limiting process involved in that. We want to concentrate on the outcome, actually getting the value of the origin, rather than the process. So here's how you set that up. There are several aspects to it. So what I'm going to do really is write down the definition or axioms for a class of generalized functions, a class of distributions which are going to include the delta function. It's going to capture the essential nature of the delta function, and it's actually going to, as it turns out, include much more. All right, so there are several aspects to the definition. 1. This is the definition of generalized functions or distributions. Distributions. Distributions, all right? So first, you start out with a class of test functions. So you start with what are called test functions. Now, when the Fourier transform comes back into the picture, this is going to be the class of rapidly decreasing functions. But for other problems, you might consider a different class of functions. But generally speaking, these are the sort of best functions for the properties you're worried about. All right? So you think of these as the best functions. I'll call them phi. All right? Best functions for the problem at hand, for the given, let me just say, area of application. All right? So again, for Fourier transforms, it's going to be the Schwartz functions, the rapidly decreasing functions. For other functions, it may be those functions which I mentioned last time of compact support, the functions which are actually not just tending to 0 outside some finite interval, but which are identically 0 outside some finite interval. All right? Then 2, associated with these test functions is a class of what are called generalized functions or distributions. All right? A distribution, I'll call it T, is a linear operator on the test functions that produces a number. So one says in the biz it is a linear functional. A distribution T is a linear functional, I'll say what this means in just a second, functional on the test functions. All right? What that means is I give you, or you give me, for a test function phi, T of phi, T operates on phi, produces a number, and it's linear, is a number. Typically you allow complex numbers here. And T is linear. That is to say, T of the sum of two functions is T of phi 1 plus T of phi 2. And T of, it obeys the principle of superposition. T of alpha times phi is alpha times T of phi. I'll get out of the way in just a second here. All right? So a distribution is a linear operator on the class of test functions. You start by defining the class of test functions that somehow is going to have all the nice properties you could possibly imagine for your problem. A distribution, or also known as a generalized function, is an operator on those functions that produces a number. And the final property is you don't want to give up taking limits completely, because limits do come into the subject. And so you assume that these linear operators are continuous in the following sense. 3, the final property is a continuity property. That is, if phi n is a sequence of functions which converges to a function phi, then that implies that if I operate on it with one of these generalized functions or distributions, that converges to T of phi. I'll say more about this in just a second. Actually, this is the most problematic part of the definition. But I'll say more about it later. Okay? The continuity property means that if you have a sequence of test functions that are converging to another test function, if phi n converges to phi, then that implies, that's supposed to be an implies, that if I operate on this sequence with a distribution with a generalized function, that produces a sequence of numbers. So on the left-hand side is a convergence of a sequence of functions. That's hard, actually. And again, I'll come back and talk a little bit more about that later. On the right-hand side is just a sequence of numbers. That's easy. It's easy to talk about a sequence of convergence of a sequence of numbers. So these numbers converge to that number. All right. This is because you don't want to abandon taking limits completely, because it does come up in the applications. All right. Now I want to introduce a little terminology here and notation that's used in this subject, and that is you often say that a distribution is paired with a test function. Instead of saying it's operating on a test function, that's what's going on. You often say it's paired with a test function. And again, you'll see a reason for this in just a second, a reason where specific pairings that come up. And you often write a notation for the pairing is often written like this with angle brackets. T is paired with phi. This notation is supposed to just indicate it's an alternate notation for writing T operating on phi. Both notations are in use. This notation is probably a little bit more common. All right. This is not an inner product. All right. It's supposed to indicate that T is somehow operating on phi to produce a number. And the operation is linear. If I take two functions, T of phi1 plus phi2 is T of phi1 plus T of phi2, and T of alpha phi is alpha times T of phi. All right, I know there's some deep waters here, but when you see how this works and when you see how effectively you can compute with this, it's really quite stunning. It was not so easy to do. I mean, this was adopting this point of view to give a rigorous foundation for delta and then actually to also develop the Fourier transform, I mean, was no less maybe comparable, no less revolutionary, maybe comparable to the whole shift from like classical mechanics to quantum mechanics. It required a different point of view. You had to look at things differently. You have to do it. Well, do you need quantum mechanics or not? I mean, it's a more accurate description of the world at certain scales. Well, theory of distributions is a more accurate way and a more effective way of dealing with the problems you really want to deal with. It's just the way it is. All right. Now, again, let's go back and recover delta. So let's recover delta in the context of this definition. Of this definition. All right, so what is delta doing operationally? Delta operationally is that what is the outcome of applying delta? It is to pull out the value of the function at 0. At the end of the day, that's what delta is supposed to do. You wrote down this nutty integral. We, everybody, wrote down this nutty integral. And I'm not exactly trying to talk you out of it. I'm just trying to say that there's another way of looking at it that makes more sense. Right. So operationally, the effect of delta is to pull out the value of the origin, is to evaluate the function, a function at the origin. All right. So you say that to yourself a couple times. Operationally, the effect of delta is to evaluate the function at the origin. All right. The mathematical modus operandi is turn the solution of a problem into the definition. I say to myself, that's how I should define delta. Define delta. According to this definition, which I'm erasing now, on test functions, it's supposed to be a linear functional on test functions. How is it defined? You give me a test function. I have to tell you how delta operates on it. Yeah.
Else. I thought the function it's paired with not the same as the function it operates on. You kind of suggested the same.
No, I mean. I don't know what you thought, but this is what I'm saying. Okay, I mean this is a common notion of pairing. Okay, that is, the phi is a given test function. T operates on the function phi. So instead of writing T operating on phi, which is sort of a functional notation, you just often write this notation as an alternative. And it's very common. You actually also see this in physics when they talk about bra vectors and ket vectors. You know, a bra vector operates on a ket vector. I hate saying that. I feel ridiculous saying that, especially when I have no idea what I'm talking about. But you know what I'm talking about if you've had a physics course. Same thing, one sort of vector pairs with another kind of vector in physics. And here, an operator pairs with a function. There's a class of functions that it operates on. This is the operator. All right, and what I'm saying is the use of the word pairing there is appropriate. I mean, that's what's said. All right, now, like I say, let me go back to delta here. So you say to yourself, well, the operational effect of delta is to evaluate a function at the origin. Turn that into a definition. Define delta by delta paired with phi is what? Bless your souls. Phi of 0. Phi is a class of test functions. That is given to you. You give me a test function, I have to tell you what delta does to that test function. And then I have to verify that it satisfies the properties of a distribution. I say delta operating on phi is nothing but phi of 0. All right, now, is it linear? Well, what is delta paired with phi 1 plus phi 2? That is phi 1 plus phi 2 at 0 by definition. That's what delta does. It evaluates phi 1 plus phi 2 at 0. But that is, of course, phi 1 of 0 plus phi 2 of 0, which is delta paired with phi 1 plus delta paired with phi 2. That is delta paired with phi 1 plus delta paired with phi 2. And similarly for the scalar multiplication property. All right, how about continuity? How about continuity? Again, without saying precisely what I mean by a sequence of functions converging, what about this statement? That a phi n converges to phi in a sense that you just imagine. So a sequence of functions converging to another function, does that imply that delta phi n converges to delta of phi? Or, excuse me, I'll use the pairing notation here. Does that imply that delta paired with the sequence phi n converges to delta paired with phi? Well, write out both sides. What is the left-hand side? What is delta paired with phi n? Delta paired with phi n is just phi n of 0 by definition. Well, if the sequence of functions phi n is converging to phi, then surely phi n of 0 is converging to the value at 0. All right? If phi n converges to phi, then surely phi n of 0 converges to phi of 0. And so surely it must be the case that delta paired with phi n operating on phi n converges to delta operating on phi. So it's continuous. It's a continuous linear functional. Okay? Now, I want you to think about this a little bit and I hope appreciate it really, because this mysterious delta function that was defined by these ridiculous properties, it's 0 everywhere except at one point where it's infinite, its total integral is equal to 1, and it pulls out the value of the function when you integrate it against it. I mean, those ridiculous properties have been, in effect, captured in the simplest possible distribution. All right? This complicated limiting operation that we talked about in terms of concentration operationally is defined completely airtight by evaluation at 0. All right? The simplest sort of operation, evaluate at 0. And that captures this mysterious notion of delta. It's very impressive. Now, if that was all you could do, you say, that's a lot of work, and I want to completely change my worldview, so you can define this one little distribution that I was perfectly happy taking limits of anyway, and I know those statements were bullshit, but I'm happy enough with bullshit. I can tolerate ambiguity. Why do you really put me through this? And the fact is that it goes far beyond this particular example. The fact that it captures this particular example so easily and so effectively is already a good thing. But if it were the only thing, it would have withered on the vine. All right? But it doesn't. It allows us to define very robustly Fourier transforms and everything else. And we'll get to that. Not right now, but we will. Let me give you one other slight version of this. You have also probably seen a shifted delta function. In your work with delta functions in other classes, you have also probably seen I imagine, some statement that looks like this. The integral from minus infinity to infinity of delta x minus y, f of y, dy is equal to what? F of x. All right? You've probably seen statements that look like that, right? Delta sifts through the values and so on. Okay? And now that statement is, to use a phrase, never mind. All right? That doesn't make any sense. What do you want to define here operationally? You want to define a shifted delta function. All right? If this is the delta function based at the origin, based at 0, delta applied to phi pulls out the value at 0, what do you want to define to capture this statement? Precisely, as a distribution. You give me a test function, I tell you what the pairing should be to pull out the value at number x. So what do you define? What do you want to define here? Tell me what the distribution, give me a name for a distribution and tell me how it operates. Don't be afraid. Nothing bad will happen. Not the boards are not going to fall off the wall or anything like that if you get it wrong. You want to capture this property. You want to capture this property of a shifted delta function, right? Or don't think of this, I mean, I know you're trying to think of this in terms of convolution, probably. Don't think about it in terms of convolution. Just think about operationally trying to pull out the value of the function at some other point other than the origin. What is the distribution that will do that? Define a distribution that will do that. I can wait. Right. All right. So I define, it's a different distribution. All right. So define, let's say delta sub A as a distribution by the formula delta sub A paired with phi is phi of A. Okay? So the case we had before was when A is equal to 0. Now, is that linear? Is that continuous? You can check, but it's the same idea. All right, so delta of A this defines delta A as a distribution. You give me a test function, I have to tell you how the distribution operates on that test function to produce a number. What do I tell you? You give me phi, I say delta A operating on phi produces the value at A. Period. Airtight. Airtight. All right? No ridiculous statement like this. No limiting processes involved, nothing. All right? It is a straight definition based on what you want the outcome to be. Okay. Now, all right, so take a deep breath. Hold it. Exhale. Good. Now, I claim that we have gained something. We've certainly gained something in clarity here, or rigor if you want. I mean, this mysterious delta function has now emerged operationally as the simplest possible distribution. But oh, the struggle. I mean, I had to introduce these complicated things and so on and so on. You want me to change my whole point of view, and that's asking a lot of me, and so on, and why, Lord, why? One question you might well ask at this point is, have you lost anything? All right? I mean, yes, you've defined delta, so we've gained delta. But have we lost anything? All right. What I mean by this is, ultimately, the test functions are very restricted. All right. The test functions might be a very restricted class. These rapidly decreasing functions, they don't include, constant functions. They don't include the rectangle function. They don't include the triangle function, and so on. I mean, how are those functions going to get back into the scene? How are, e.g., the rectangle function, the triangle function, trig functions, etc., going to come back in? How are they going to come back into the picture? I mean, delta is this bizarre thing, and true, it was defined in a pretty simple way, but, I really want to get to the point where I can consider the functions that I really want to consider, triangle functions, rectangle functions, sines and cosines, and so on. Can I consider those in the context of generalized functions? And more to the point, when we get to it, can I consider those in the context of actually taking Fourier transforms? Because that's what I want to get to. I want to get to defining more general Fourier transforms. So the Fourier transform of delta is going to make sense. So the Fourier transform of constant functions is going to make sense. So the Fourier transform of sines and cosines is going to make sense. I mean, how can I do that? If I can't do it classically by an integral, how can I do that in this context? Or can I do it in this context? All right. So I want to explain now how generalized functions include, in a natural way, the sort of ordinary functions. That is to say, I haven't lost anything. I haven't lost those functions that I really want to consider. They're there. They are in there, but they're in there in a slightly different way. So you can consider, so this is a question of how to consider ordinary functions in this context. All right? So again, I want to consider, for instance, the constant function 1. So e.g., how to consider the constant function. Take a very simple function, the constant function 1, as a generalized function or as a distribution. Okay? All right, so now you buy the premise, you buy the gag, all right? You want to consider this as a distribution. What does that mean? It always means the same thing. If you want to consider something as a distribution, that says you give me a test function or I give you a test function, you have to tell me how your new thing here is operating on that test function. All right? So how do we pair? So given a test function phi in whatever class you're considering, how do we define a pairing? Define a pairing of 1 and phi. All right. Well, it's actually very simple, but it's again maybe not one of those things you would. It takes its cue from really how these things grew out of the classical applications and the classical view of things. I'm going to define it by integration. So to pair 1 and phi, I have to get a number. A distribution operates, I say this over and over again, and this is what you have to say to yourself. A distribution operates on a function to produce a number. It has to be linear, it has to be continuous. So 1 has to operate on phi somehow to produce a number. And the pairing is by integration. That is to say, you give me phi, I have to tell you how 1 pairs with phi. And here's my definition. 1 pairs with phi as the integral from minus infinity to infinity of 1 times phi of x dx. A lot of big build-up for a very simple definition. But, sorry, that's what it is. Okay? That certainly produces a number, and if phi is a good enough function, this integral is going to converge. Different values of phi will give me different numbers. All right, so in some sense, I know all about 1 if I know all about these integrals for different values of phi. There's nothing about 1 you can ask me somehow that I can't answer if I integrate it against different sorts of functions. Of course, there's not much you can ask me about 1 that I can't answer anyway. But operationally speaking, there's nothing you can ask me about 1 that I can't tell you if you allow me to integrate it against any old test function phi. All right? More generally, how does more generally, or more generally, but the same way, by the same token, I want to include the rectangle function, the triangle function, everything else, and consider those as distributions in the same way. So likewise, for e.g. the rectangle function. The rectangle function pairs with the test function by integration. Integral from minus infinity to infinity, pi of x, phi of x, dx. Phi of x may be very smooth. Pi of x is not smooth, but the product makes sense and the integral makes sense. All right? That's my definition of how pi pairs with phi. That identifies pi, the rectangle function, as a distribution. This definition identifies, or defines, I should really say defines 1, the constant function 1, as a distribution. Now you can check, integration is a linear operation. So linearity works. So does continuity. That's a little bit more complicated, actually. That requires certain limiting theorems for integrals, but never mind. I mean, I'm setting some of those details aside right now. And in general, same thing for trig functions, say. So how about sine of 2 pi x? All right, that function you can't integrate that function from minus infinity to infinity. But you can integrate it if I pair it with a function, say, that is decreasing. By definition, sine of 2 pi x can be considered as a generalized function if I tell you how it operates on a test function. How does it operate on a test function? It does so by integration. The integral from minus infinity to infinity, sine of 2 pi x times phi of x dx. All right? The integral sine of 2 pi x doesn't make sense. That integral doesn't converge. But if I multiply it by a function which is dying off, the integral will converge. All right? So for the purposes that I'm going to want to consider, sine of 2 pi x can be considered as a generalized function. It's a real honest-to-God function. But for these purposes, it can also be considered as a generalized function because I can tell you how it operates on test functions. It operates by integration. All right? Again, seems like a lot of, God, I mean, there's a lot to absorb here. And are you really going to, you're really been able to do anything with this? And just, you have to go along for the ride a little while longer, and then you'll see how this works. Because it's really, how you actually see how to compute with this is really, I think, pretty impressive. All right, so in general, many very wild functions can be, and some not so wild functions can be considered generalized functions by this pairing. So if f of x is any function, I won't say, I'll put quotes around any, because not all functions, it's not the case that for all functions the integral will make sense. But for many of them, you can consider f of x as a generalized function or distribution by defining its pairing. F paired with phi is the integral from minus infinity to infinity, f of x, phi of x, dx. F operates on phi by integration. All right, and that's a linear operation. Now again, for not all functions will this integral converge. All right, but that is for not, I mean, you can stick in a really wild function here and maybe it's not going to work. But for most garden variety functions, and more than most garden variety functions, for things that can be pretty wild, that sort of integral will make sense because the test functions are so nice. The nicer you make the test functions, the more wild functions you can stick in here. All right? And for Fourier transforms, we're going to find that the Schwartz functions as test functions are just the right class. They're the ones that are going to allow us to include sines and cosines and deltas and all sorts of things like that. All right? So one says in this context that a function determines a distribution. How does a function determine a distribution? You give me the function, I have to tell you how it operates on a test function. It operates by integration. And then you really have to say, all right, that operation is linear, that operation is continuous, that all is okay. That all works out fine. And so we haven't lost anything in the sense that the class of generalized functions includes all the functions that society needs to function. No play on words, no pun intended. All right? All right, so next time, we'll wrap it up now. Next time, you're going to see how this comes together to define the generalized Fourier transform and more. All right? See you then.